All right. 8.5, graphing reciprocals of quadratic functions now. So, using the information from 8.4, the math lab, we're now going to apply that. We're going to take it a little bit further. Okay. But we're going to use a lot of the same strategies that we did in 8.3. So how many vertical asymptotes does the graph here, do these ones have? Vertical asymptotes is what you looked at in 8.4 a bit. Well, however many NPVs there are for the denominator is how many vertical asymptotes you're going to have. So always want to have it in factored form for the denominator. Okay, so x plus 2, if we look at our NPVs, we would say x plus 2 cannot equal 0, so x cannot equal negative 2. And x minus 7 cannot equal 0, so x cannot equal positive 7. Those are your NPVs. Your vertical asymptotes are just based right off of those again. So then your vertical asymptotes is going to be x equals negative 2 and x equals 7. Asymptotes are always an equation, an x equals 2 or a y equal 2 if it's a horizontal asymptote. So there are two different asymptotes there because there's two factors for the denominator. X plus 5 squared, well, that's just meaning we've got x plus 5 and x plus 5 again. You're going to get the same thing, so there's going to be only one asymptote, which is x plus 5 equals 0, so x equals negative 5 is your vertical asymptote. The NPV was x cannot equal negative 5. Okay, so using that graph there to do the reciprocal, we're going to take it step by step again through. Step number 1, wherever the original zeros are is where you're going to have a vertical asymptote. So vertical asymptote at original zeros. All right, original zeros up right there. So let's put in a vertical asymptote. Step number 2. You want to draw the line y equals 1 and y equals negative 1 to get your invariant points. So your invariant points at y equals 1 and y equals negative 1. So wherever it crosses the line, y equals 1 and y equals negative 1. So that would be here and there. We've got to go through those 2 points. Those are invariant points. We'll put them on there. And then we can start graphing to the left and to the right. So step number 3, draw graph to left and right of the invariant points. Alrighty. Okay. So from this invariant point to the left, the original red line goes up to infinity. So we're going to do the opposite. We're going to still go to the left. We're going down to 0. We cannot cross the axes. You cannot cross the x-axis. The original function does never get to infinity, so we will never get to 0. And it's nice, smooth curve. To the right of that function, the original is going down towards 0, so we're going to go up towards infinity. Do not cross the asymptote. Nice, smooth Curve, no scalloping. Okay, so don't cross the asymptote. Then we go to the next invariant point. To the left of that invariant point, the original function is going down towards 0. So we're going to do the opposite. It goes down, we go up, still to the left. It goes down to 0, we're going up to infinity, don't cross the asymptote line. And then the last section, to the right of that invariant point, the original is going up towards 0. So we're going to go down. Oh, sorry, it's going up towards infinity. We're going to go down towards 0. Do not cross the x-axis. Let's just make a note of that. Never cross the asymptotes. So that means your vertical asymptote, which was your NPVs, in this case, it would be at x equals 1. That's your vertical asymptote. So you can never cross x of 1. And you can never cross the x-axis, because that's the horizontal asymptote. So never cross the asymptotes. Vertical, which is your NPV locations, and your horizontal, which is always going to be for you your axis. Horizontal, which is your x-axis. Okay, so of course this question could have been done by using table of values, finding some points on the red line, and then graphing the reciprocal of that point for the y value. Taking the y value, doing the reciprocal, and graphing that point. And that would have been an okay method to do it as well. So as you're going through 8.4, the math lab, you should have come up with some connections there. And that connection should have been that you could have 0, 1, or 2 vertical asymptotes for any quadratic function. The reason for that is it comes exactly back to the same thing. If we're doing the reciprocal of a quadratic function, the number of asymptotes is exactly related to the number of zeros. And we did that in the quadratics chapter. We used the discriminant to find out how many zeros are there going to be. How many factors are there? How many times is it going to cross the axes? And you had 0, doesn't cross the axes. So if the original quadratic doesn't cross the axes, there's not going to be any asymptotes. If there's 1 asymptote, there would have been 1 0 for the original. And then if there's 2 original zeros, then there's 2 asymptotes as well. And this is what the shapes would look like. For the first one, with no vertical asymptotes, you're just going to get kind of a curve that's just above or just below the x-axis. The way that these ones get made is if we had an original quadratic that did not have any zeros. Original quadratic with no zeros, then you get a reciprocal with no asymptotes. Or it would be like this if it was below the axis. That would have been the original shape. What would it look like if we have 1 asymptote? This is what the graph would look like. For the reciprocal, well, the original then would have been crossing at 1 and -1. It would have been a quadratic that was just tangent to the axis. Or opening down, that would have been fine as well. Just tangent to the axis. Remember that any of these intersection points is at a y of 1 or a y of negative 1. And then the third shape with two asymptotes. So this is where we would have a graph that was originally a parabola with two zeros, a 0 here and a 0 there. Remember that the original 0 is where you're going to have the asymptote happening. So we would have had an original 0 here, and let's say there's y's of 1, y's of negative 1. We would have had a parabola that looked something like that. That would have been the original function. Or opening down, but again, going through the two asymptotes, coming up and going back down. Okay, so right to next there in the column, to think further, what property do all the graphs possess? Well, they have the same property that the original quadratics had. An original quadratic has a line of symmetry. It's symmetrical. It has vertical symmetry. Because it has vertical symmetry, so does its reciprocal. So they all have a vertical axis of symmetry. So they all have a vertical axis of symmetry, just like the original quadratic had. But they also have another one. And that is that they all have a horizontal asymptote at y equals 0. Because you cannot get a reciprocal function to equal 0, it's going to have a horizontal asymptote at y equals 0. Okay, so in order to sketch a graph of the reciprocal of a quadratic function, there's a few things that we want to always be looking at first of all. So we want to know what the vertex is of the original quadratic function. So for original quadratic, which is the denominator, we need to know where the vertex is. We want to know where the x-intercepts are. Y-intercept is always a good thing to know as well. And then we're also going to want to know what is the value when y equals 1 and when y equals negative 1. Okay. Those are the invariant points, that last part. So these are the things that we want to look at from the original, and they're going to really help us to sketch the graph of this one. All right, so let's start by getting the original quadratic on there. The vertex of, we'll deal with y equals negative x squared minus 1. Vertex of this one is going to be at 0, comma, negative 1. All right, let's put that on there. 0 and negative 1. Right here. And we also know that it's opening down. So this is going down. Well, if it's opening down and its vertex is already below the axes, then there's going to be no x-intercepts. Y-intercept is the negative 1, so we know that as well. So then, when is it y equal 1? Oh, it's not going to happen. None. It's never above the axes. What's the value when y equals negative 1? Well, that's going to be x equals 0. That's going to be an invariant point. So the original function looks like that. If we don't have any asymptotes, because there's no original zeros. We don't have anything crossing y equals 1, but we do have an invariant point at y equals -1, and that's the point right here. And then we start drawing from there. Same way that we drew in 8.3, or sorry, in 8.3. To the left and to the right of an invariant point. I actually know this value. It's invariant, so we know that it's part of it. To the left is going down towards 0, so we're going to be going up towards infinity. And it curves. Does not cross the axes, though. Putting an arrow on the end because it goes on forever. This had an arrow on going forever as well. Then to the right, it's also going down to infinity, so we're going to be coming up towards 0, but not crossing the axes. We can never cross the axes. And that's what the graph would look like. Show you what it looks like in a perfectly drawn one, just like that. It's a nice, beautiful curve. So another option to drawing these, and some of you may feel a little bit safer doing so, is find some points on the original quadratic. Pick an x of -1, x of -2, x of -3. See what you get for the y value. For instance, if you took x of -2, plugging it in, you'd get -2 squared, which is 4. And then a negative gives you -4, minus 1, -5. So at -2, it would have been -5. Take the reciprocal of that -5, -1/5, and plot the point. Do the same thing with some positive values. Plug them in, see what you get, and plot those points. And that might help out. Okay, so this next one, we look at it, we know that there's one NPV, so there's going to be one asymptote. The asymptote is going to be at the NPVs of x equals -2. Because that's the 0 of the original function. So we want to know where's the vertex, again, of the original y equals -x plus 2 squared. Want to know the vertex, we want to know the zeros, x-intercepts. Y-intercept is always a good one to know as well. And we want to know when y equals 1 and y equals -1. Plugging all those things in really helps out. Let's get the original one graphing in here. We know that it's opening down. Because of that negative right here. We also know that the vertex is going to be at -2, 0. The x-intercept, which we identified right over here, is x equals -2. And then the y-intercept. So for the y-intercept, you plug in for the original here, plug in 0 for the x. 0 plus 2 is 2, 2 squared is 4, -4. So your y-intercept is when y equals 4. Sorry, -4. And then what happens when y equals 1 and y equals -1 on the original? So if we look at plugging in a y of 1, that would give us 1 equals -x plus 2 squared. Divide over the negative, then we take the square root. But we can't take the square root of the negative number, so at y equals 1, it's never going to equal y equals 1. So let's go with y equals negative 1 and see what happens there. Okay, divide over the negative, so we get 1 equals x plus 2 squared. Square root, taking the square root, it's plus or minus square root of 1. So now we get square root of 1 is plus or minus 1. X plus 2. Subtract that over. X equals negative 2 plus 1. And x equals negative 2 minus 1. So it's going to be two places that we have the negative 1. And that's negative 1 and negative 3. Let's start putting all this together on the graph with the original. Vertex negative 2 and 0. We know that x-intercept is the negative 2 because we're crossing right there. Y-intercept of negative 4. And a y equals negative 1 at negative 1 and negative 3. Join your dots. That's what the original looks like. But now we need to do a reciprocal. Step number 1. Any original zeros is a vertical asymptote. There's an original 0. We've got a vertical asymptote in there. We can't go 1 over 0. Step number 2. Finding your 1 and negative 1. There is no y equals 1 on here, but there is the y equals negative 1, invariant point there, invariant point there. Got to go through those. Let's work left and right of the invariant points. To the left of this invariant point, the original graph went down, so we're going to go up to the left. It went down to infinity. We're going up to 0. Do not cross the axes. To the right of this invariant, it went up to 0. We're going to go down to infinity. Do not cross the axes. We're done now. Let's go to this invariant point. To the left, it's going up to 0, so we're going to do the opposite, down to infinity. To the right, the original is going down to infinity, so we're going to go up to 0. Do not cross the axes. Nice curved lines. Do not scallop them. Make them nice curved. And that's done. Show you what the actual graph should look like. So notice that we've got about the asymptote, right there we've got two sides that are symmetrical. Because the original quadratic was symmetrical about the line of symmetry, about the vertex, we're going to have symmetry about the vertex, where the vertex was on this one as well. Because the vertex was at the axes and gave us our asymptote at the vertex, it's going to be symmetrical. So we can draw one side and then flip it right over top of the line of symmetry and draw the other side as well. And so that's how you can use symmetry to be able to graph one of these. Graph one side, then graph the other side. Okay, so sketching the graph of this one. Again, first thing we want to do is let's get the original quadratic drawn. Negative x minus 1 and x plus 1. This is in factored form. We can see that it's opening down because there's a negative in front. Opens down. We need to know the x-intercepts, the zeros. It's already in factored form, so we can just take the zeros, x-intercepts, zeros, right from here. So that would be x equals 1 and -1. The vertex is going to be halfway in between those two. So vertex is always halfway in between the two x-intercepts. Halfway in between is when x equals 0. A little bit easier to do it this way than to expand it and complete the square to find the vertex. So take the two intercepts halfway in between x is 0. Well, plug 0 back in and see what y value we get. So then y equals -0 minus 1, 0 plus 1, just -1 times 1 equals 1. So our vertex is going to be at 0, 1. Y-intercept now. So the y-intercept that we have so y-intercept is always when x equals 0. Hey, we just did that. So we know that the y-intercept is going to be at the y of 1 again. Same place that the vertex is. All right. Noticing that we have two original zeros, that means we're going to have two asymptotes on this graph. Let's plot that up. Vertex, start there. 0, 1. Right here. X-intercepts of 1 and -1. Right there. Y-intercept, we already have. We know that it opens down. Yeah, that makes sense because it's the only way to connect these points. There's our original function. Now let's start drawing our reciprocal. Our reciprocal is always going to be, well, first of all, start. Where are the original zeros? At the original zeros, you have vertical asymptotes. Here's an original 0. Let's put a vertical asymptote in there. Here's an original 0. Let's put a vertical asymptote in there. I'm just going to re-straighten my axes here. Beautiful. So that's step number 1. At the original zeros, you have vertical asymptotes. Notice that we had 2. Step number 2, at y equals 1 and y equals -1, we've got invariant points. Here's y equals 1, touches right here, and we've got y equals -1, right through there. That's step number 2. So now let's find out where are all of our invariant points. I've got one right here. I've got one right here. I've got one right here. 3 invariant points that we're going to work with. Start with the one on the left. To the left of this point, the blue line goes down towards infinity, so we're going to go up towards 0. Never ever cross the 0. Cannot cross the x-axis. To the right, it's going up towards 0. We're going down to infinity. Do not cross the asymptote line. I'm going to go right up to this one. This is the vertex. So to the left of this vertex, it's going down towards 0 originally. I'm going to do the opposite, go up to infinity. The original quadratic was symmetrical right at the line of symmetry, which goes through the vertex. I can take what I just drew and just flip it over top of the line of symmetry, which is at, this time is at the y-axis. It's wherever the vertex is. Flip it over the vertex. So I know that it's going to just look like that on this side. Or, going through the motions again, The original blue went down towards 0, so I went up to infinity, not crossing the axis, or sorry, the asymptote. From this one here, it's going to look just like the flip of the one on the left side. But just go through the motions. To the left, it goes up towards 0, so I'm going to go down towards infinity. To the right, it's going down to infinity, so I'm going to go up towards 0. A nice curved line. And now you've got it sketched. The black line is your original, or is your reciprocal function. Okay. Any part of the original graph that's above the x-axis is going to be above the x-axis when you draw it. Any part of the original that's below the x-axis is going to be below the x-axis when you draw it. So if there's any portion of the graph that's above the x-axis, it's still going to be above the x-axis when you do the reciprocal. If there's any portion that's below the x-axis, the reciprocal is also going to be below the x-axis. All right, example number 4 there. Working backwards. Again, playing the Jeopardy game. When we look at the first one, we're trying to draw the original quadratic function. In the first one, a here, the whole thing is above the x-axis. So we're going to be drawing totally above the x-axis. We don't draw anything below the x-axis. Wherever there's an original asymptote, now in this one, or wherever there's an asymptote, there was an original 0 on the quadratic function. So an asymptote becomes a 0. We know we have to go through that point. Because there's only one asymptote, there's only one 0. Well, the only way for that to happen is if that's the vertex. We also know that it's symmetrical about the vertex. So if that's there, this has to be the vertex. Then we look at, there's nothing going to be at -1, but there is going to be something on +1. So wherever y equals 1, we're looking for invariant points. So I know I have to go through there, and I have to go through there. We've got a y-intercept that's way down here below 1. So I'm not sure exactly what that is. Maybe it's 1. Do they actually tell us? No, they don't tell us. Would have been nice if we would have known what that y-intercept is, because then I could just take the reciprocal of that number and drawn it up. Okay, well, I'm just going to have to assume that it's, I don't know, let's just say that it's 1/6. So then we'll just make that +6. So if this was 1/6, that would have been 6. If this was 1/5, that would have been 5. If this was 1/4, it would have been 4. I'm just going to say it's a 1/6. They don't really give me enough information. But then we're going to do a nice curve here to make the quadratic that goes through there. There's your original quadratic. Same with B. Working backwards. Those asymptotes were original 0s. Wherever the graph crosses 1 and -1, we've got invariant points. So now I got here, here, there, and there. I also know that it's symmetrical right along here. So my vertex has to be along this line somewhere. And they give me a point. They actually give me the y-intercept this time. They're saying that it's 0,1/2. I'm going to take the y number, the y coordinate, and do the reciprocal of that. If it was 0 and 1/2 on this one, the reciprocal of it would be 0,2. So that's where my vertex is going to be, on the reciprocal of the y-intercept number. Any number that you know, you can just take the reciprocal of the y, and that's another point. Now let's just combine and join all of our points. And there's your original quadratic. and then just finish up by answering your discuss the idea questions there.